solve for R, this is what you get.
That's the radius of the growing crystal.
If you assume the nucleus to be spherical, you assume the inside of the nucleus to be homogeneous, the fluid outside the nucleus to be homogeneous, the surface area to be constant energy difference on the interface between the two, the nuclei to be perfectly spherical, gamma being the per area energy penalty for that area, delta mu being the per volume benefit, and depending, the actual value of delta mu depends on where you set 0 and stuff, but it's the difference between the free energy being in the state inside the nucleus and the state of the fluid. And if those things are all consistent, and this is the density, the number density.
Also neglect curvature effects of the interfacial tension, and
that's what you mean by the gamma being constant. Gamma is constant over the area, and doesn't change as the nucleus grows. So these are the assumptions made for classic nucleation theory. The classic nucleation theory refers to the state where you're making these assumptions. Everything's nice and uniform everywhere, everything's continuous, and the values don't change as the nucleus grows. And if you, and there's a whole bunch of crazy stuff, the next slide doesn't have a bunch of crazy. Sorry. Mac PowerPoint to Windows PowerPoint. We should have tested this. So the probability of getting past this critical, so R squared would be the nucleus, the size of the radius of the nucleus at the point where it becomes more favorable for it to grow. And if all these assumptions are made, you can find the difference in free energy at this, this free energy barrier at the maximum point, and say that, well, the probability of forming this nucleus is going to be an Arrhenius type function of the, so an exponential function of the free energy and over the fluctuations in the system, whatever native fluctuations are happening in the fluid system you're starting with.
I'm sorry. So this is the Gibbs free energy?
This is the free energy difference in whatever units your delta mu in. So it's usually going to be the Gibbs free energy, but you can sort of set up whatever ensemble you want. It's the free energy that you've measured based on whatever difference you know between the volume of the volume of the growing cluster, volume of the growing nucleus, and the volume of the. So I don't know if that would necessarily be a Gibbs free energy or not.
It's described as Gibbs free energy because in an NVT simulation, the formation of a nucleus separates the density, so you make like the overall density of the system is constant, but you end up with a pressure drop, so you go through multiple thermodynamic states.
But there's no requirement that this be an NVT ensemble.
Not really. And in the infinite limit, it gives in the Helmholtz free energy. In this case, if the nucleus is small with respect to the system size, should be equivalent.
Okay. Thanks.
I should call it F, but the literature doesn't.
Okay. The literature calls it doesn't. Well, because it's mostly an experimental thing. So if you want to make assumptions and you know the chemical potential of your starting phase, and you know the chemical potential of your final phase, you can make the assumption that's the difference between those chemical potentials, which I think would usually be known as Gibbs free energy, but I don't know if that's the case. All right, so you have a probability of forming this, of getting to the top of this energy barrier that's proportional to how high the energy barriers is and the thermal fluctuations. In the system, the probability of the probability of nucleating, which is denoted as I, is some prefactor. It's called the prefactor times. This is the value that was in those missing equations. This is this. This is delta G star over KBT is the same as this. Delta G star was missing on the previous page, but it's the same thing. So it's just saying that this is I is proportional to the probability of forming the crystal, also proportional to that, and the proportionality is captured in this kinetic prefactor. This is also part of classic nucleation theory, where that prefactor is not always, but often written as a product of three different terms. One is the density, or one is the density in the fluid. So how likely are there to be particles there able to attach? the probability of this is the probability of hitting the nucleus. And it's a function of the self-diffusion constant, measure of the average distance particles are from the average distance travel. The average distance particles are from the nucleus, sorry, and the nucleus, the amount of area they have to attach to. So the number of particles in the nucleus to the two halves is roughly the number of surface particles. So it's approximation of how many sites there are for a particle that's joining to join on. So there's this part of the kinetic term is the probability of something attaching, which, yeah, diffusion length, diffusion rate, and number of sites to diffuse to. And then Z is something that's slightly more complicated. Z is the Zeldovich factor. Is what it physically represents is the curvature of this free energy at the peak, roughly. So if something is at the peak, this peak isn't actually going to be perfect. So the likelihood of it going this way or the likelihood of it going this way depends on the curvature. And I'm not going to go into this in much detail. You can look at the various references and then at their references, or you can actually, the wiki article on this is pretty good. But it has to do with the change in the free energy as the cluster grows. The curvature of the particle could be captured in that, but it's not in this formulation. All right. So you can calculate a lot of things based on making those assumptions, and these are used for practical reasons a lot of the time. In reality, though, there's a lot of terms in here that you don't know. Some of them you can measure and some of them you can't. So in reality, you have a system where you're not going to know, in experimental systems, you're not going to know the positions of all the particles. You might not even know the distribution of the positions of all the particles. So in reality, what you have is a system where you're measuring a couple of order parameters, say the density of your system and some refractive index that might give you an indication of the crystallinity. You define your initial state is this shaded region A, and your final state is some shaded region B based on your order parameters. But to actually go through the transition, what you're going from is one energy well. So these lines are free energy isosurfaces. So you're going from one energy well to another energy well. And it gets complicated to measure these things in practical sense because, as indicated by the difference between this path connecting one energy well to the other energy well, and this path, which on paper connects state A to state B, but does not actually go across the energy barrier because it's only in state A to begin with on paper. It's actually already past the big energy barrier, and that's one of the problems with ideal system. In real systems, all of those assumptions that you made are never quite true. From a broad view, sometimes they're true. They're true enough for classical nucleation theory to be useful in a lot of places, but really, nuclei are never perfectly spherical. The energy of adding a particle to a forming crystal is not the same at all points because it's crystal facets. And there's fluctuations in the both inside the forming crystal nucleus and in the fluid surrounding. So there's a lot of papers that deal with this. When you go into reading the papers, so this the critical nucleus, as defined based on classical nucleation theory, is this very clear-cut size where there's a peak when you balance the surface tension to the volume, and you can define it very clearly. In practice, the critical nucleus is the nucleus where the probability of crystallizing is 50%. So in practice, you would bet you would go the other direction. In some cases, say in polymerization studies or whatnot, you measure a bunch of clusters that are forming and count how many of them grow. In any sort of forward flux type or transition path sampling research, they do something similar. So this is kind of a dense plot, but what this is each dot, and this is a very similar method to the methods I use, so each dot represents a starting state of a simulation. The x-axis is how big the largest cluster was in that system. The y-axis is how likely that was to crystallize from there. The reason it looks stripy is because if you started from a certain point and did 20 trials, the smallest probability, the probability of progressing is going to be increments in increments of 1/20th. So you have lines there, and clearly they have extra samples for some of these because some of them fall outside. Which doesn't, it's just explaining that that's an artifact and that's a perfectly acceptable artifact. So you can see that there isn't one specific critical nucleus, right? If there was one specific critical nucleus, you would have one nucleus that fell at 0.5. Rather, there's a range from 150 or so to nearly 400 in the size of the particles that have a 50% chance of nucleus. They calculate the critical nucleus size to be 243, which is plotted here as a dotted line. But even there, clusters of that size have a wide range. And that's going back to this idea that the size of the nucleus n is not the only order parameter at play here, right? The space that this is happening in is not two-dimensional. So then the next question is to look at what else comes into that, what else is important in nucleation. And this gets to the idea of we've talked about different order parameters to use. And so this is a pretty interesting plot that shows, this is the crystallinity on the inside of the cluster size, and these are all pointed, these are isoenergy lines on here. And so what this is showing is that the nuclei that have roughly 50% chance of forming, some of them are really large, but the ones that are really large can have a really low crystallinity, relatively low crystallinity. The ones that are smaller, you can have small compact structures that are a lot more stable. And that's what's not explicitly said in here, but what's shown by the isoenergy plots too, is that these actually have a lower, the free energy difference is greater because you have a lower free energy because the crystal is better.
So are they defining, so how are they even defining crystal if it's not by this Q6? Is it density based or something?
It's a little bit more, it's
a solid liquid order parameter.
It's a variation of the solid liquid order parameter.
So it's just like how much I resemble my neighbors.
It's how much my local environment resembles the local environment of my neighbors. But then this takes just the particles that were in the cluster and has their average.
Okay.
For 6, not matching it. You have to read the paper to get the details of it.
I couldn't find the paper, so I didn't add it to my section either. But there was a paper where they did nucleation growth in the Ising model, and the second order parameter they used was, like, if you use cluster size, that's one thing, but you can also use the parameter of the cluster.
The average value of the parameter of the cluster.
Just up or down.
The number of particles that have the up or down interface. Because the spin Ising model has a nucleation point rate. If you put them all up and have a field that comes slightly down, they won't flip. But so if you track cluster size, you get noise like this, but you track it as a function of cluster size and parameter, which is the analytical actual energy of the cluster, of course. Then it fixes the data. But you don't strictly need to track the parameter, but you get the noise distributions. Like
Perimeter, not parameter.
Parameter.
The
Perimeter.
surface area and two.
I'm just gonna
The perimeter. So yeah, that's, you can do the asphericity. And the idea being that these multivariable order parameters get you closer to a reaction coordinate. But this is a way to say what's actually important. Another study that looked at these sorts of things did a couple of things where they looked at their fluid with several different order parameters. They found clusters, critical clusters and post-critical clusters at lower density and higher density, and compared the surface is, and they went on to define to talk about the different, not just whether or not the inside's crystalline, but what sort of crystalline shape did it take, whether or not the structure on the inside was congruent. These are not hard spheres, by the way. These are soft spheres that at higher pressure will form BCC. In case anyone noticed that and thought it was weird. They used only the Q6 and Q4 to differentiate between the different structures, and didn't come up with anything that was a nice, clean multivariable order parameter type thing, but they made a lot of the idea that the inside of these structures were found to be HCP. This is another one of those things where they weren't really good about differentiating between HCP and FCC, because, well, these are highly subject to noise, and while this looks very clean, I wonder what a time average thing would look like for these. But it's interesting that where they show this. In many cases, when someone says FCC, they are not distinguishing between FCC and HCP, and I think you're going to talk about that later. So when you're talking about the nucleation, there's this sort of what is nucleating. It's not actually ideal. Another thing along the same sorts of lines, they took the same order parameter but with much more relaxed cutoffs to look at the fluctuations in the fluid. And they did something really interesting where they have these pre-nucleation, they had an acute acronym for them that I can't think of now, but pre-nucleation structure, dynamic heterogeneity. They called it dynamic heterogeneity in this supercooled fluid. What they're looking at is regions where the order parameter would pick something up if they set the cutoff very relaxed. And they found that if they tracked so each color is a different density, and if they tracked how many nuclei they counted over time, then how many of these clusters that are pre-critical clusters they counted over time, they were able to use that to estimate what the nucleation rate would be, assuming that the nucleation rate from the pre-nucleation clusters was consistent, and they actually came up with values for nucleation rates that were close, that matched, that over-predicted experimental results for spheres, but came a lot closer than simulation results that have been done, which I thought was pretty interesting. Because that's a big thing, is that simulations are all self-consistent, and this low pressure, this very low driving force range for hard spheres, but they're not consistent with experiments. So that was pretty interesting.
They're only off by 10 orders of magnitude.
But they get the right curve.
Yeah.
And what they suspect is that the reason why the experiments have a lower rate is that the experiment is slightly polydispersed in a way that's not measured. And actually, no, it is measured. The polydispersity of the experiment is noted, and that's what they're saying that's what they're suspecting the difference is. Do you have this?
I've read it before, but I also found that part weird because polydispersity in general, which I talk about later, is shown to harm nucleation.
Yeah, that's what they're saying. That's what they're saying. Their system does better than the experimental results that are.
Yeah, their system's faster, not slower.
Their system is perfect. The polydisperse system is slower.
Isn't that axis faster as you go up? Like the hour of freckles are the lowest nucleation rates on there.
Yes.
And that's monodisperse. Polydisperse should be slower, so it should have like 10 to the minus 30th or something horrible.
Yeah. So the blue is these guys. The green is the experimental results, which are polydispersed.
Oh, yeah.
And the polydispersed ones are lower.
Okay.
Remember, because Frankel and Arrow did the whole polydispersity thing to try and correct, but they found the polydispersity hurt it, so it corrected in the wrong direction.
Yeah.
Right? So afterwards, these guys come and made their estimation, which is higher than the polydispersed one.
Yeah. I still think the suspicion to me is that the experiments aren't homogeneous nucleation ever. But
it's a separate question.
Yeah.
But it's but the
Sorry, you had 22 minutes.
Okay, so I'm almost done. Another different approach to it that's completely outside of nucleation and growth is instead of looking at what happens in the fluid, look at the permutations of clusters that are available. So these guys counted the possible identifiable finite clusters for sizes from 5 to 11, for numbers of particles from 5 to 11, for things that are fixed, so static and isostatic. They have enough contacts. These are hard, sticky spheres, by the way. They have enough contacts that they can't rearrange themselves or more. So that's the number of contacts. And there's different numbers of microstates counted by microstates that are not congruent with the system and microstates that are congruent with the system, or with the crystal, as in the Barlow ones are ones you could fit into whatever crystal into a crystal that could form and fill space, whereas these ones could not fit into a crystal that could grow and fill space. And I'm a little bit anyway. And so for the clusters of 11, here they show all the different macrostates, and by macrostate they mean the set of all the nearest neighbor distances is the same. And count how many of them there are and which ones have different rearrangements, have different microstates associated with that macrostate. And so they're saying that the ones that have different ways to form are going to occur more often are just going to occur more often because there's more ways to find them. So in the ones where there's a whole lot of there's a whole lot of microstates that can form, so this is for 11. Most of them are not congruent with the crystal structure that would form. So they're trying to predict how likely a nucleation type of thing is to happen by saying how many of the ways can things come together, how many of the ways that things can come together are consistent with the crystal forming. And by counting these, they can figure out how entropically favorable or disfavorable a nucleation event is. So that was a completely different approach. It's kind of interesting. Going from nucleation to growth, just another note on how things are not isotropic, and in reality, different facets grow at different rates, and you can control and you can add things into the system that specifically inhibit growth on different facets. So that's how a lot of the polyhedral nanoparticles that our experimental collaborators work with are actually made by using ceramics that have, this isn't ceramics, this is gold nanoparticles, but you can use ceramics that have different growth facets where you can inhibit different growth facets and get polyhedral nanoparticles. And a lot of that stuff is captured in thermodynamics by this paper that I like to talk about, where what they're talking about is the energy sort of situation for the black line is classic nucleation theory. But if you have some other pre-nucleation, like some other arrangement in the fluid that can happen, it can drastically change what the effective barrier to nucleation is. Say if there are larger clusters of some other organization that can come together, then rather than having to nucleate with this disfavored surface arrangement, if there's an arrangement that has a very small penalty or no penalty at all for forming in the fluid, that can easily, so martensitically or something, transform into the structure you want, if that phase can form first, and then has an easy time transitioning over to the phase you want in the end, then that can help you. But the same type of process can hurt you too if the system tends to form clusters that are not consistent with what you eventually want to form, because then you have an even larger step to get over. That's all I've got to say. There's some interesting notes about the pre-nucleation factors actually depending on actually being activated processes as well. But you can read about that yourself. That's it. Cheers.